Are you able to see my screen now? Yes?
Yes, sir.
Yeah. So have you all tried with this question? Last time we discussed, you try by yourself. Have you tried this question? Anyone? Harminder?
डेरिवेशन देखी है एज इन क्वेश्चन नहीं ट्राई किया
ठीक है, कोई बात नहीं। और कोई? शुभम? शुभम मेरा?
Yes, sir. Good morning, sir.
ट्राई किया क्वेश्चंस को?
ट्राई किया था वो बस आया नहीं लेकिन आंसर।
अच्छा ठीक है। पीयूष? पीयूष?
यस सर। सर मैंने भी अभी डेरिवेशन नहीं देखी, ट्राई नहीं किया।
ठीक है, कोई बात नहीं, डेरिवेशन देख लिया ना। ठीक है, तो डेरिवेशन के हिसाब से अगर आप चलोगे, सो इन दिस क्वेश्चन दे आर आस्किंग you have one block that is having dimension 25, 25, 150, okay, and that is being pressed using flat die, okay, flat die and open die, you say. So, and it is been squeezed to 6.25, and since it is been squeezed, wait, so let's say you have this bar, okay, column, you say block, this one. So it is having this one, let's say this like that. Okay, so it is being pressed using your die punch, upper ram and bottom ram. So usually it is being fixed and this is moving, and using this you are applying pressure on this. So what happens is, this is, it is saying 25, 25, 150, and it is being pressed to 6.25. So this is your, this length is 25, okay, this length is 25, and this one is also your 25, okay, and if you see your this length, this is your, according to it, this is 150, okay. Now since you are applying a pressure P, okay, so once you are applying this pressure, it will get squeezed and it will have shape like that. Are you understanding this point? It will go up to here and you are applying pressure using this ram. It will move now till this point, okay. So now it is being squeezed from 25, this length 25 to 6.25, okay. Is that clear? This is what the value is, you see. And once you are trying to squeeze it, this part, this length will get elongated. Yes. So it is getting extended because of your transverse force. So now it became from 25 to 100. Is that clear?
yes
Is that clear? Yeah. And this part, if you see, they are keeping it constant, 150. So there is no change they are considering in this axis. Okay. So it will remain same 150. Okay. You don't go with the length what I am representing here. This is 150 you consider. Okay. It is in like it's 150. So it is not changing. So according to this, it is changing only in two direction. Okay. One is y direction and another one is, let's say, x direction. So it will be it will be condition of plane stress condition, okay, where it is moving only in one plane, xy. Is that part clear to everyone? Yes, batao beta.
Yes, sir.
Yeah, so the same, now I took this from the book only. So since 150 dimension does not change, deformation is plane strain condition. So to establish, now here is your equation which we are considering for, when we are considering this equation comes for, now you all have gone through the derivation, so can you let me in which condition you are getting this equation? Harminder?
सर क्वेश्चन नहीं समझा एज इन प्लेन स्ट्रेन कंडीशन में प्रेशर निकालने के लिए वी कैन यूज दिस
Yeah, so in this condition, when you are choosing sticking condition, you please remember this part, okay? When you are going with sticking condition, we have, even in the plane, if you see, let me go to the, yeah, here. If you see, this is when you are considering it is continuously moving, okay? When you are placing it between the ram and you are applying pressure, if you are considering plane condition, okay, where it is moving, okay, then you will have pressure like that, okay. So in this condition you are getting it in exponential form, okay. But when you are going to sticking condition, where it is hard to move, where if your sticking stress is higher than your deformation stress, your material will not have any deformation, okay. So in that condition you will have sticking condition. This is your sticking condition and this is your sliding condition, okay. ये ठीक है, ये ठीक है.
यस सर
Yeah, so accordingly, if you see, this is first they are considering for sticking condition, because in sticking condition, if you can remember this, you are getting this will be getting in exponential form, okay. And if you are getting for going for sticking condition, you will be getting it in linear equation, okay, where you will have m plus c like that equation, okay. So this is what you are having, you see. ठीक है बेटा?
यस सर
Yeah, so here first we'll start with sliding condition. So in sliding condition, what we are getting? We are getting 2 sigma by root 3 exponential 2 by 2 bracket in bracket 2 mu by h. Who is having mic on? Please mute yourself, everyone. Yes. So if you consider this point, so first we are considering pressure required, pressure distribution at each x point, okay. So this is what you are getting here is, you'll be getting it as, if you have, see, if you are putting x equal to 0, no movement, x equal to 0, then you will have maximum condition, x equal to a, you will have minimum condition. X equal to a means this complete part will become 0. 0 means e to the power 0 means 1. So you will have, at least always you will have some pressure required, okay. Okay, for sliding condition at the free surface. So always you will have some value first, then you are having your curve, okay. This is the condition you are getting when you are applying pressure at a bar, okay. So here you will be getting maximum pressure, P max. I'm using mouse, so it will be a bit rough, but please try to understand. It is P max, okay, at the center of the line, okay. Here you are getting maximum stress, maximum pressure required. So pressure distribution will be like that. So at the center line of the slab, you will have P equal to, Here this equation has not mentioned, but the same thing they are considering value of sigma naught, and then mu it is given. H you are changing from let's say 25 to 6.25. So this is final condition you are taking, because you are considering the pressure required. Sir, class hai. So you are considering pressure required at the center when it is being pressed to 26.25 from 25. So we'll be putting here the value 6.25. Okay, this will be value of your H, and X will be 0 when you are considering at center line. Okay, ये समझ में आया यहाँ तक?
Yes, sir.
Yeah. So from here you will be able to calculate P max. P max will be equal to, let's say, we'll be having 435 megapascal. Okay. So it will be coming 435 megapascal. Now, if you want to check, like you need to check pressure distribution from center line to free surface. Okay. So first at center line x equal to 0. So center, this is, you see, this complete part is, you are starting x from here. Okay. And it is moving towards here up to value of a. This half part you are considering, this is a. Okay. So at center x equal to 0, and at the free surface x equal to a. Okay. So at center x equal to 0, and at free surface it will be, you are going up to, you see this value you have 100. It get extended up to 100. So this complete part is how much? It is 100. Okay. Complete is 100. It means half is 50. Yes. ये clear है? Clear है सबको?
Yes, sir.
Yeah. So the same value we'll put here, and we'll try to get value of P at each point. Okay. At each distribution. So you'll be considering a different length, and you'll be getting P value as 8. Okay. Now if you go for sticking condition, it will be Ti equal to mu P. Okay. So you are considering here mu P. Now you got the value of P at each point. So you calculate the value of Ti equal to mu P. So if you check this, once you have calculated, so you can see Ti, this is for sticking condition. Now it is reducing with the when you are moving towards free surface. And again, if you consider for pure sticking condition, the value of K become K equal to sigma naught by root 3, and sigma naught by root 3 equal to, you are getting 3.98. So this is 3.98. Now you calculate Ti value where it is 3.98. So it is in between your 37.5 to 43.75. Yes, you check this value. Where this value will fall? Here, somewhere. Yes. बताओ बेटा. समझ में आ रहा है ये? If you remember your derivation is tau equal to mu p. याद आ रहा है सबको? हरविंदर.
Yes, sir.
Yeah. Piyush. Piyush. Piyush, are you there? Piyush has left the class. So who else have gone through the recordings? Derivation? Anyone? राघव
हाँ जी सर।
डेरिवेशन देखा?
हाँ जी सर।
सो व्हाट यू फाउंड हियर?
हाँ सर, वो टाउ इक्वल टू म्यू पी के इक्वल, और फिर वो उन्होंने सिग्मा की वैल्यू निकाल ली है, और वो फिर एक्स देख रहे हैं किस एक्स के अंडरलाई कर रहा है।
ठीक है, देन फ्रॉम हियर यू विल बी एबल टू कंक्लूड दैट when you are going for sticking friction, okay, so at what x actually your sliding is getting lower, ठीक है? so ये x point बताता है. so if you see from 0 to up to 50 you are actually working under your sticking friction condition. समझ रहे हो? up to 5.4 or up to 37.5 or even more you will have sticking friction condition dominating. ये क्लियर हो रहा है?
Yes, sir.
Yeah, so from here it will be concluded like, okay, when once you are going to calculate, okay, once you are going to calculate your complete P require, so you can directly consider most of the part is being deformed under sticking friction condition, okay. So once you come to know most of the part, yeah, most of the distance is covered in sticking friction condition, so you directly you can calculate force required. See, now you have to calculate total forging load. So total forging load you can calculate directly using the equation for total friction, total sticking condition, okay, not to total sliding condition. This has been calculated, this is has been shown just for this purpose only, okay. So you see up to here 3.98, okay, it is being lied here. So up to here your sticking friction condition is dominating, okay. So in that case if you go for for sticking friction condition, if you calculate your P max will be 71.7, okay. So in this condition when you will be calculating, so we already have given the formula where you can calculate actual x. Here we can see it is lying between 5.4 to 3.3, but we also have seen the equation, okay, where we can calculate value of x1. x1 equal to a minus h by 2 mu ln 1 by 2 mu, okay. So using this equation you can directly find out, you know the value of h, okay, you know the value of mu, you know the value of a, so you can calculate that x is coming 41.3. so from 41 when you are seeing this graph, okay, this graph and this graph, okay, this graph when you are looking, it is your x value you are getting, this x value is 41.3. yes, समझ में आ रहा है बेटा? बताओ. You remember this equation, this equation we have seen in derivation. What is the value of x where under this sticking condition will lie, out of this sliding condition will lie. So this equation, that x1 value we have seen, this is the formula to calculate the value of x1. So from here you can see 41.3 out of 50. If up to 41.3 you are going with the sticking friction condition, so you can directly calculate your force required, first minimum force using sticking friction condition, okay. So here is based on 100% sticking friction condition we are assuming, okay. So you can calculate P average using sticking friction condition and it will be coming like that. Then you can calculate P into area on which it is acting, ठीक है. So you can calculate load required. ये clear हो रहा है सबको?
Yes, sir.
Yeah, and in case if you want to calculate actual condition, what you have to do is you go with the P average and P average you can calculate by integrating it from 0 to, let's say, 41.3 using this equation, okay, plus 41.3 to 50 using sliding condition. ठीक है, ये क्लियर हो रहा है? ये क्लियर हो रहा है सबको?
Yes, sir.
Yeah, so this is what you have to put this equation. And if you are assuming, let's say it is 41.7, consider 100% distribution using sticking friction condition, then you can directly calculate using this. If you are not going to consider complete, you are not going to assume it like, okay, 100% deformation is under sticking friction condition, then in that case, from 0 to 41.3, 0 to 41.3 or here up to here, it is 41.3, it is dominating sticking friction condition. So you have to derivate this equation from 0 to 41.3, integrate it, and then integrate from 41.3 to 50 sliding friction condition equation. ठीक है बेटा, सबको क्लियर है ये? Yes, here you can put P value will be, you go to the derivation, then it will be more clear. Sigma naught dash, okay, A minus X, no, it is for that condition, sigma naught dash, then it will be like P dx. P dx means you have to put your value sigma naught exponential, wait, here I am writing again, P equal to sigma naught dash exponential 2 mu by H A minus X. Okay, so this will be your equation that you need to put here, and you need to derivate from 41.3 to 50. You will be changing the value of X. ठीक है बेटा, क्लियर है सबको? जल्दी बताओ.
Yes, sir.
ठीक है, इसको एक बार और प्रैक्टिस कर लेना. ठीक है, then we already have discussed this one. Now we will see the closed die forging. In closed die forging condition, it is like, okay, it will be like, as we have calculated force and everything for open die, similarly you can consider here, but here you will see the empirical formula. Actually it will not be like you are going to see the derivation. So in closed die forging it is a bit complex because everything is going inside your a closed die. Okay, this is very complex and designed for the intermediate steps to make a final precision. So usually in closed die forging condition we are going with preforming condition. Okay, so here we can consider we'll have like, okay, you preform it. Okay, for if you try to remove the if you try to reduce the machining part, so better in this condition before going to forging you go for preforming condition using the powder metallurgy route. Okay, so you'll be have preformed condition that you'll be pressing again in your die punch setup, so the cutting part, machining part will get reduced. Also the sharp edges or whatever the things you are going, a complex structure you want to get, it will be difficult if you are going with simple bar, and if you want to go for that complex condition, then stress will generate more and residual stresses will be more. It can go for fracture and everything. So in that condition we have to go with the preforming condition, so that you can read and you'll be understanding. So these are the parts, okay, where like in closed die condition there are three classes actually. Okay, so on the basis of their structure, actually given different structure, they have been divided in three class: class 1, class 2, and on the next slide it is class 3. Okay, in closed die condition. So if you go with the first class, in first class also, class 1 also, you'll have मैं कितनी देर से क्लास लेफ्ट हूं, कोई बताएगा? हिमांशु,
Yes, sir.
कितनी देर से मेरा क्लास लेफ्ट है? अभी मैं देख रहा हूँ क्लास लेफ्ट दिखा रहा था मेरा, मैं क्लास लिए जा रहा था।
सर 15 मिनट होंगे सर।
15 मिनट से?
Yes, sir.
सो क्लोज डाई फोर्जिंग में जो हमने अभी बताया अभी कि फोर्स रिक्वायर्ड, यू आर एबल टू लिसन और नॉट दिस वन, दिस पार्ट? कहां तक सुनाई दिया आप लोगों को? मुझे नहीं पता। ये पार्ट हो गया हिमांशु, वानी, अनिका,
Yes, sir.
ये हो गया था। दिस इज सिंपली क्लासिफिकेशन ऑफ योर क्लोज डाई फोर्जिंग आई हैव डिस्कस्ड। ये हो गया था कंप्लीट?
Sir, nahi.
ठीक है, ओके। सो विल सी हियर। सो दिस इज द शेप class we have decided, like okay, class 1, class 2, class 3, okay, and it will be again subdivided in 101, 102, 103 according to their subsidiary element added to your simple shape. And shape class 1, class 2 has been divided or categorized as when you are having L equal to B equal to H, it will class 1. Class 2 means L equal to B, but it is far greater than H, then it will be class 2. And if L is greater than B and greater than B is greater than equal to H, in that condition it will fall in class 3. So if you have listened up to here, so it will be same like okay, here also it is being like okay, classified as per their principal shape element. Long it again, it will have 3, 3, 2, 3, 3, and in 3, 1, then 3, 1, 1, 3, 1, 2, 3, 1, 3. Principal shape element with straight axis. It is, if you go for 3, 2, 3, 2, it will be longitudinal axis of principal space with curvature. And if you go for 3, 3, you will have 3-dimensional change. Okay, in 3 direction you are changing. So accordingly, you will be calculating your, you will be categorizing your closed die forging class. Okay, and then if you want to calculate the forging loads required for closed die forging, so it has been like okay, you need not to go with the open forging derivation. Here people have given their or as per their experience, they have given some empirical formula. That empirical formula is like okay, P equal to sigma S AT into C1, where C1 will be the constraint factor. Okay, the constraint factor means you see here you are giving different shape. According to different shape, you will be having your value of C1, and it is changing from 1.2 to 8. Okay, as per the difficulty of your complex shape. And you can see from here like okay, if you want to simply, if in general, if it has been given like okay, its cross sectional area is A, okay, and its deformation stress value is sigma, so calculate the force required to deform it. So usually people what they do is sigma into A, okay. But if you see, if you are changing the shape, okay, if you are having some changes in the shape, your value changing from 1.2 to 2.5. Even for smallest, like simplest form, if you consider here, even for simplest form, it is not simply what you are calculating using this equation. It is having C1 value 1.2. Yes, in closed die forging. Are you able to hear me?
Yes, sir.
Yeah. And if you go for complex condition, see, even it is 8 times higher than what we are getting from here. If you are going for let's say 3-dimensional condition with complex shape, okay, even this force required, forging loads required is 8 times higher. Okay, so it is not very simple like okay, if you are going for closed die forging, and you can say like okay, if you want to change it from here to here, you simply calculate with the final shape or final dimension the value of force required. It will not be that easier that you are thinking. Especially for closed die forging, it can go up to 8 times, and simplest shape requires 1.2 times more force as you are calculating using this equation. So C1 is having 1.2 means it will be multiplied by factor 1.2. Yes, is that part clear? Am I audible?
Yes, sir, it is clear.
Yes. So then we'll see the forging defect. So there are like several type of defect you can have in your forging, because you will be having like you are applying pressure somewhere else and it is getting deformed in somewhere else. Okay, so in that condition, inhomogeneous pressure stress distribution will be there. So according to that, mainly three type of typical forging defects has been found. First one is cracking at the flash. So that flash you are giving, okay, the flash you are giving to let the extra material flow. Okay, so you know, like, okay, if you are giving that flash and if your value of h, this, okay, this h is less, it requires very high pressure to let the material flow inside. Okay, so why it is less? So that if you are having more material to get deformed, and if you don't want that, then it will get flowed from here, but it should not get flow from here directly. That's why it is being given less. Okay, but if you are putting it very less, it will have very high stress over this point. Okay, and because of that, your material can have crack at the flash. Okay, so it is cracking at the flash, and then when you are going to machine it, okay, when you are going to machine and remove this part for uh, final structure, this crack can flow towards your part as well. Are you understanding this part? Yes. मैं बता रहा कि आप जब ऐसे कॉम्प्लेक्स से बना रहे हो बेटा, तो इसमें आप फ्लैश प्रोवाइड करते हो जहां से मटेरियल फ्लो हो जाए इजीली. ठीक है, आपका मटेरियल यहां से फ्लो हो जाए अगर आपका एक्सेस मटेरियल फोर्जिंग में है एंड यू डोंट रिक्वायर दैट वन. ओके, ऑलरेडी थोड़ा सा फ्लैश दिया जाता है सो दैट अगर आपका एक स्ट्रेस लेवल बड़ा ज्यादा हो गया जितना आपको चाहिए, तो इसमें वो ना रहे और वो मटेरियल यहां से फ्लो हो जाए. बट इसको हम बहुत ज्यादा ओपनिंग भी नहीं रख सकते हैं, अदरवाइज मटेरियल कैन फ्लो डायरेक्टली फ्रॉम हियर एज वेल. तो इसलिए इसकी थिकनेस कम रखते हैं. जितना थिकनेस कम होगा उतना ज्यादा हाई स्ट्रेस रिक्वायर्ड होगा मटेरियल को फ्लो होने में. ठीक है, तो इन दैट कंडीशन वी आर प्रोवाइडिंग फ्लैश विथ स्मॉलर थिकनेस. बट एट द सेम टाइम क्या होता है कि चूंकि यहाँ से बहुत हाई प्रेशर, बहुत हाई स्ट्रेस के साथ यहाँ पे मटेरियल फ्लो होता है, तो यहाँ पे क्रैक्स जनरेट होने का चांस बहुत हाई रहता है इन योर मटेरियल. सो ये जो क्रैक यहाँ पे जनरेट होगा, क्रैक जो यहाँ पे जनरेट होगा, वो क्या होगा कि आपका फिर जब आप इसको मशीनिंग के टाइम पे कट करके निकालना चाहोगे, ये क्रैक इसमें भी इलोंगेट हो सकता है. एंड इन दैट कंडीशन योर actual required part will have some crack or defects in your part. ये ठीक है, समझ में आया?
Yes, sir.
Yeah, similarly if you go for cold set, it is like when you are applying too much pressure and और आपका ये जो SAR पेज है ये बहुत ज्यादा है, यहाँ पे material flow नहीं हो पा रहा है. So in that condition also, because of that cold set, you are getting some cracks at SAR pages of your surface. Similarly, you will have internal cracking due to secondary tensile stress. ये इस कंडीशन में होता है कि जैसे आपने ओपनिंग कर दी, अब यहाँ से आपने स्ट्रेस अप्लाई किया तो आपका सेकेंडरी स्ट्रेस जनरेट होता है इधर इस डायरेक्शन में. ठीक है, सो ये जो सेकेंडरी स्ट्रेस होता है, अगर आपको याद हो कंडीशन, जब आप टेंसाइल स्ट्रेस करते हो तो उसमें सेवरल स्टेजेस होते हैं, है ना. उसमें क्या होता है कि पहले स्मॉल स्मॉल क्रैक्स जनरेट होते हैं, फिर they will get connected to each other and then they will have some form like that and it will fracture the surface. Similarly, you see in this direction it is getting opened, okay, because of this secondary tensile stress. ठीक है, so this type of cracks also can be seen in case of forging because of secondary tensile stresses. ठीक है, ये क्लियर है? Yes, जल्दी बता दो बेटा.
Yes, sir.
Yeah, so now we'll have the last part, powder metallurgy forging. In powder metallurgy forging, we have some advantage of improved material utilization, because again here powder metallurgy forging means first you are, if you want to give, let's say if you want to give some complex shape to your structure, okay, so you'll be simply putting it in a die, okay, and you are simply by using some polymer or some binder, you are giving this complex shape to your material. Okay, now in this condition you are not letting your material flow to these cavities. Okay, so this is what is powder metallurgy. It is not like you will have a bulk material and you are trying it to flow towards this shape. Okay, here powder metallurgy forging means you are giving a pre-compact to your material like that, and then you are forging it to reduce the porosity and let the material flow, and you get a good shape. ठीक है, समझ में आ रहा है ये क्या हो गया पाउडर मेटलर्जी फोर्जिंग? यहाँ पे हम बल्क मटेरियल के साथ डायरेक्ट नहीं चलते, हम पाउडर मटेरियल के साथ चलेंगे, जिसको हम एक प्रॉपर शेप प्रोवाइड कर देंगे यूजिंग अ डाई पंच, सिंपली बाइंडर एंड, जैसे आपने समझ लो कि आपने सिरेमिक में किया था कि पाउडर लिया, उसको क्रश किया, देन उसको हल्का सा प्रेस करके एक पर्टिकुलर शेप दे दिया, फिर उसको सिंटर किया, तो वहां पे तो सिंपली हमने पैलेट बनाया था. In that condition you can have this type of structure and you simply give a proper, like you give a small pressure so that you will have that particular shape, then you go for forging. ठीक है, so it reduces your elimination of machining, okay, to final size, because you already have this final shape. ठीक है, समझ में आ रहा है बेटा?
Yes, sir.
Yeah, then also here your plastic deformation is very much dependent with your porosity. So during plastic deformation your porosity is closed up and eliminated. Okay, so it is like, okay, your material will have that high residual stresses, that is you are applying to flow through this, will get reduced, though because of pores you will have, definitely you can have more brittleness, but that you can remove using several practice and using some proper criteria, proper procedure, you can reduce this part, and because of this porosity, the brittleness you are getting, you can remove that part. But at the same time, residual stresses generated because of the forging and very high residual stresses which can generate the cracks at the sharp edges, that can be reduced. Yes, समझ में आ रहा है?
Yes, sir.
Yeah, then you can calculate, there are basic plasticity mechanics for porous powder metallurgy. This is the last part in this chapter. So here if you see the Poisson ratio, the relationship between densification and plastic deformation is achieved through relating the plastic Poisson ratio nu to the fraction theoretical, okay, density. So this is your density you are getting, and this is theoretical density. So using this formula you will have value of nu, and at the same time if you go with the frictionless formula, frictionless condition, where this is rho, this will be your, wait a moment, this is not rho, yeah, this is rho. Okay, so this is, again this is also rho, so you'll have minus rho equal to whatever the change, actually if you want to see, that will be coming from strain in each direction, like, okay, in longitudinal x y z you say, okay, so it will be changing in each direction, accordingly it will be having your this equation. Again if you go with the definition of Poisson ratio, so what is Poisson ratio? Poisson ratio is actually, what is Poisson ratio? First you try to understand. Let's say you are applying pressure here, okay, any pressure, and it is changing from, let's say this is L2, it is getting changed to L1 to L2, okay, and at the same time if you see, this is also getting changed from W1 to, now it is W2, okay, So Poisson ratio will be in which direction you are applying pressure. Okay, change in this direction will fall, like strain actually. Okay, so it will be delta L by L1, and here it would be in another perpendicular, that you are applying pressure in one direction but it is getting change in another direction. That change you are considering. Okay, so it will be delta W divided by W. ठीक है, समझ में आ रहा है क्या होता है पॉइसन रेशियो? So
Yes, sir.
it is actually new change in lateral direction, and here it is change in axial direction. Okay, so axial direction means in which direction you are applying pressure, and this is lateral direction means another direction. Okay, so this will be your new. So that's what you can see here. So it is showing like, okay, d e r d e theta will be equal to nu d a z. So e z means in this direction you are applying. So if you go with this one, it will go to here. Okay, so in lateral direction el will be e axial into nu. So that's what you are getting here, and these are the strain in another direction. So if you put this for equation here, first you can calculate it from dp by b. This will be the value. This value you have to put here in this equation. You will be getting formula like that. Okay, so this is what you have to get. What is the strain you are getting when you are going for plastic mechanics for porous powder metallurgy, and at the same time, when you will be going with this one, you will have, like, simply you cannot go with the von Mises criteria. You will have some additional part here. Okay, because of plasticity of porous part. So you will have, see, the first part is simply von Mises criteria, and second part term will be account of porosity. Okay, through Poisson ratio. So this will be your complete equation from where you can calculate the value of stress required to deform your material. ठीक है? This only you have to memorize. ठीक है बेटा? ठीक
Yes,
है?
sir.
Yeah. Any doubt? You please read, है ना? Otherwise difficult हो जाएगा बेटा. ठीक है, आप लोग थोड़ा सा रिवीजन करो, और कोई डाउट हो तो पूछो. डाउट होने पे मैं बताऊंगा, बिल्कुल बताऊंगा, जितनी बार पूछोगे. बट ऐसे रह जाओगे तो फिर आपको दिक्कत होगा ना फाइनली मार्क्स उठाने में. है ना? सही है?
So.
ठीक है. ओके.
थैंक यू सर.
ओके. टेक केयर.